Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How evolution would work on other worlds. Evolution is not a theory specific to Earth. It is a fundamental principle that must operate wherever life exists, as inevitable as gravity or thermodynamics. The basic mechanism is elegantly simple. Organisms that are better suited to their environment tend to survive and reproduce more successfully than those less well suited, passing their advantageous traits to offspring. Over countless generations, this process of natural selection shapes organisms to fit their environments with remarkable precision. Charles Darwin recognized this principle in the 19th century by studying finches on the Galapagos Islands and countless other organisms, but the principle extends far beyond Earth. On any world where life emerges, evolution would be the engine driving biological diversity and adaptation, though the specific outcomes would be shaped by each world's unique conditions. The fundamental requirements for evolution are remarkably minimal. Life must be able to reproduce, creating offspring. There must be variation among individuals. No two organisms are exactly alike. Some of this variation must be heritable, passed from parents to offspring, and there must be differential survival and reproduction. Some variants survive and reproduce more successfully than others. These conditions create evolution automatically, inevitably, as surely as releasing a ball on a slope causes it to roll downhill. Any replicating system with heritable variation and selection will evolve, whether it's based on DNA, some other information storage molecule, or even non-biological replicating systems. On Earth, DNA serves as the information storage medium for nearly all life. The DNA molecule consists of two strands wrapped around each other in a double helix, with each strand composed of a sugar phosphate backbone and a sequence of 4 bases: adenine, thymine, guanine, and cytosine. The sequence of these bases encodes genetic information, and this information is copied when cells divide, passed to offspring when organisms reproduce. Mutations, random changes in the DNA sequence caused by copying errors, radiation, chemical damage, or other factors, create the variation upon which natural selection acts. But DNA is not the only possible genetic molecule. Scientists have created synthetic alternatives called XNAs, xenonucleic acids, that can store information and be copied, yet use different sugars or even different backbone structures than natural DNA and RNA. These artificial genetic molecules demonstrate that information storage and heredity don't require DNA specifically. An alien organism might use a completely different molecule to store genetic information, perhaps based on different chemistry more suited to its world's conditions. A very cold world might favor genetic molecules that are stable and flexible at low temperatures. A very hot world might favor molecules that resist heat degradation. The specific molecule doesn't matter. What matters is that it can store information, be copied with reasonable but imperfect fidelity, and allow variation to arise. The timescales of evolution would differ dramatically on different worlds. On Earth, bacterial generations might span minutes to hours, allowing rapid evolution. The bacteria that cause diseases evolve antibiotic resistance within years or decades, as antibiotics create selection pressure, favoring resistant strains. In contrast, large organisms with long generation times evolve more slowly. Elephants with generation times of decades evolve far more slowly than bacteria, On an alien world where organisms have extremely long lifespans, perhaps living for thousands of years, evolution would proceed at a glacial pace from a human perspective, with significant changes taking millions or billions of years. Conversely, on a world where organisms reproduce very rapidly, evolution might proceed at dizzying speeds. If alien microorganisms reproduced every few minutes, like some Earth bacteria, they could evolve through thousands of generations while we watched. Such organisms might adapt to new conditions, almost in real time, developing resistance to threats or exploiting new resources faster than slower evolving species could respond. The environment determines what traits are advantageous. On Earth, giraffes evolved long necks because reaching high branches provided access to food that shorter animals couldn't exploit. Cheetahs evolved extreme speed to catch fast prey. Cacti evolved to store water and reduce surface area in desert environments. Each adaptation reflects the specific challenges and opportunities of the organism's environment. On alien worlds, different environments would favor different adaptations. On a high-gravity planet, evolution would favor short, stocky body plans with strong skeletons and powerful muscles to support body weight against stronger gravitational pull. Tall, slender organisms would be at a disadvantage because the structural demands of supporting height would be too great. Flying organisms might be rare or absent because overcoming gravity to achieve flight would require enormous energy expenditure. Over millions of generations, organisms would become increasingly adapted to moving efficiently under high gravity, perhaps developing 4 legs or even 6 or 8 for stability, with low centers of gravity and massive muscular systems. On a low-gravity world, the opposite pressures would apply. Organisms could afford to be tall and slender because less structural support is needed. Flight might be easy, favoring the evolution of wings and aerial lifestyles. Animals might leap enormous distances because the energy required to overcome gravity would be minimal. Over time, organisms might evolve increasingly delicate structures, abandoning the heavy skeletons and dense muscles necessary on higher gravity worlds in favor of lighter, more energy-efficient body plans. Atmospheric composition would profoundly influence evolution. On Earth, the transition from an oxygen-poor to an oxygen-rich atmosphere about 2.5 billion years ago, the Great Oxidation Event, was catastrophic for organisms adapted to the old atmosphere. Oxygen was toxic to them, and they retreated to oxygen-free refuges or went extinct. But for organisms that could tolerate or use oxygen, this chemical change created opportunities. Oxygen metabolism releases far more energy than anaerobic metabolism, enabling the evolution of larger, more active, more complex organisms. The size of organisms on Earth is ultimately limited by how efficiently they can deliver oxygen to their cells. On a world that never develops an oxygen-rich atmosphere, organisms might remain permanently small and metabolically limited. Without the high energy yield of oxygen metabolism, active lifestyles like those of birds, mammals, or even fish might be impossible. Life might consist entirely of small, slowly moving organisms eking out existence on the limited energy available from anaerobic metabolism. Or evolution might discover entirely different high-energy metabolic pathways based on different oxidizing agents, perhaps sulfur compounds, chlorine, or substances we haven't considered. The availability of water determines many evolutionary paths. On Earth, life originated in water, and even terrestrial organisms remain fundamentally aquatic. Our cells are filled with water, and we constantly need to replenish water lost to evaporation and excretion. On a water-rich world with extensive oceans, evolution might produce countless aquatic species, but might never develop terrestrial life if there's no advantage to leaving water. On a dry world with limited water, evolution would favor organisms that conserve water ruthlessly, perhaps evolving impermeable skins, efficient kidneys, metabolic water production, or even the ability to extract water from food or from humidity in air. Predation creates powerful selection pressures that drive evolutionary arms races. Prey evolve defenses, armor, toxins, speed, camouflage, while predators evolve counter-adaptations to overcome those defenses. Stronger jaws, detoxification mechanisms, greater speed, better sensory systems. This coevolution produces increasingly sophisticated organisms on both sides. On Earth, the evolution of predators coincides with the evolution of many complex features: eyes to detect prey, brains to process sensory information and coordinate hunting strategies, complex behaviors for stalking and capturing prey. On alien worlds, predation would likely emerge wherever life becomes sufficiently complex, driving similar evolutionary arms races, but the specific adaptations would reflect the alien environment. On a world with dense fog or darkness, evolution might favor chemical or acoustic sensing over vision. On a world with three-dimensional environments, like open water or thick forests, predators might evolve better spatial perception and three-dimensional maneuverability. On a world where prey can burrow or fly, predators would evolve means to follow them into those refuges. Sexual selection, where organisms choose mates based on specific traits, creates another evolutionary force. On Earth, peacocks evolved elaborate tails, not because those tails help survival, but because peahens prefer males with impressive tails. This sexual selection can drive the evolution of traits that actually reduce survival, but increase reproductive success. On alien worlds, whatever traits the choosing sex prefers would be amplified through generations, potentially creating wildly extravagant features that serve no purpose beyond attracting mates. Convergent evolution, where unrelated organisms independently evolve similar solutions to similar problems, demonstrates that certain designs work well for certain challenges. Eyes evolved independently many times on Earth because detecting light provides such valuable information that natural selection repeatedly favored organisms with improved light-sensing abilities. Wings evolved independently in insects, birds, bats, and pterosaurs because flight provides such significant advantages that multiple lineages evolved aerial capabilities. On alien worlds, convergent evolution would operate similarly. Any organism that needs to move quickly through water would likely evolve a streamlined body shape because physics dictates that this shape minimizes drag. Any organism that needs to see would likely evolve some structure that focuses light onto photosensitive cells, though the specific implementation might differ. Any organism that needs to manipulate objects would likely evolve some form of grasping appendages. The specific details would vary. Alien hands might have 3 fingers or 7, might be at the end of tentacles or rigid arms, might use suction or hooks instead of friction, but the basic function of grasping would emerge wherever it provides advantage. However, historical contingency, the accidents of evolutionary history, also plays a crucial role. Vertebrates on Earth have 4 limbs because that's what the early fish that first crawled onto land happened to have. There's nothing inevitable about the number 4. If a 6-limbed fish had been the first successful land colonizer, terrestrial vertebrates might all have 6 limbs today. On alien worlds, similar historical accidents would lock in features that become constraints on all future evolution. An early successful body plan might dominate an entire planet's evolutionary tree, with all descendants constrained by that ancestral architecture. Mass extinctions reset evolutionary trajectories. On Earth, the asteroid impact 66 million years ago that killed the non-avian dinosaurs allowed mammals, previously small nocturnal creatures, to diversify into the enormous variety we see today. Without that extinction, mammals might have remained small and marginal while dinosaurs continued dominating. On alien worlds, whatever catastrophes occur, asteroid impacts, volcanic eruptions, climate changes, nearby supernova, would similarly reset evolution, wiping out dominant groups and allowing previously marginal organisms to radiate into newly available ecological roles. The speed of environmental change influences evolutionary dynamics. Rapidly changing environments favour organisms with short generation times and high mutation rates that can adapt quickly. Stable environments favour organisms optimised for efficiency in unchanging conditions. An alien world with a highly variable climate, perhaps due to an eccentric orbit or an unstable star, would see evolution favouring adaptable generalists. A world with stable conditions for billions of years might produce highly specialised organisms, exquisitely adapted to narrow niches, but unable to cope with change. Intelligence itself is an evolutionary adaptation that emerged on Earth because it provided survival and reproductive advantages. Brains require enormous energy. Human brains consume about 20% of our total energy, despite being only 2% of body mass. This high cost means intelligence only evolves when its benefits outweigh its costs. On Earth, intelligence apparently provided sufficient advantage through tool use, social cooperation, and problem solving to justify the expense. On alien worlds, whether intelligence evolves depends on whether similar advantages exist. Some environments might favour intelligence more strongly than Earth did. A highly variable environment where adaptability is crucial might select strongly for intelligence and behavioural flexibility. A world where organisms compete primarily through social manipulation rather than physical prowess might favour intelligence. Conversely, some worlds might never produce intelligence because simpler solutions always work well enough. If food is always abundant and predators are absent, the energy costs of maintaining a large brain might never be justified. How evolution would work on other worlds follows the same fundamental principles that operate on Earth: variation, heredity, and selection, but expresses those principles through the unique circumstances of each world. A high-gravity planet would sculpt short, powerful organisms. A dark world might favour chemical sensing over vision. A frigid world might produce organisms with anti-freeze biochemistry and slow metabolisms. Each world would develop its own evolutionary history, branching from simple origins into complexity through billions of years of selection, extinction, radiation, and adaptation, creating ecosystems and organisms as unique as fingerprints, yet fundamentally related through the universal principles of evolution that must operate wherever life exists, proving that while life-specific forms might be infinitely varied across the cosmos, the process that shapes life, evolution through natural selection, remains constant, an inevitable consequence of imperfect replication and limited resources operating across deep time on any world that hosts living things. How gravity bends light in space. Light travels in straight lines through empty space, or at least that's what our everyday experience suggests. A laser beam shoots across a room in a perfectly straight path. Starlight reaches Earth from distant stars without deviating from its course. But this intuition breaks down when gravity becomes involved. In the presence of massive objects, light follows curved paths, bending around stars, galaxies, and even clusters of galaxies in ways that reveal one of the most profound insights about the nature of space, time, and gravity itself. The story begins with Albert Einstein's general theory of relativity, published in 1915, which fundamentally reimagined what gravity is. Newton had described gravity as a force. Masses attract each other across distance through some invisible pull. Einstein proposed something radically different. Gravity, he suggested, is not a force at all, but rather a consequence of the geometry of space-time itself. Massive objects don't pull on other objects. Instead, they warp the fabric of space-time around them, and objects simply follow the straightest possible paths through this curved geometry. Imagine space-time as a stretched rubber sheet. Place a bowling ball on the sheet, and it creates a depression, warping the flat surface into a curved shape. Now roll a marble across the sheet near the bowling ball. The marble's path curves as it moves through the depression, not because the bowling ball is pulling on it, but because the surface itself is curved. The marble is still following the straightest path it can, what mathematicians call a geodesic, but in curved space, straight lines look curved to outside observers. This is what happens with light near massive objects. The light is following a geodesic through space-time, travelling along the straightest possible path. But because space-time itself is curved by the presence of mass, that path appears curved when viewed from our perspective. The light isn't being pulled by gravity in the Newtonian sense. It's simply following the geometry of space-time, which has been warped by mass. The amount of bending depends on two factors: the mass of the object doing the bending and how close the light passes to that mass. More massive objects create deeper curves in space-time, causing more dramatic bending. Light passing closer to a mass experiences stronger curvature than light passing farther away. For most objects we encounter in daily life, this bending is utterly negligible, far too small to detect. Even for something as massive as Earth, the bending of light is minuscule. A beam of light grazing Earth's surface would bend by less than 1,000th of a degree. But consider the Sun. With a mass 333,000 times greater than Earth, the Sun creates a significant warp in space-time around it. Light from a distant star passing close to the Sun's surface is deflected by about 1.75 arc-seconds, a tiny angle equal to roughly the width of a quarter viewed from 2 miles away, but measurable with careful observations. This prediction of general relativity was first confirmed during a solar eclipse in 1919, when stars near the Sun's position in the sky appeared slightly displaced from their normal locations. The Sun's gravity had bent their light as it passed by, making the stars appear to be in slightly different positions than they actually were. This gravitational bending of light becomes dramatically more pronounced around more massive and compact objects. A neutron star containing more mass than the Sun, compressed into a sphere only about 12 miles across, creates such severe space-time curvature that light from the far side of the star can bend around it and reach an observer on the opposite side. You could theoretically see more than half of the star's surface at once because light from behind curves around to the front. Black holes represent the extreme limit of gravitational light bending. At the event horizon of a black hole, space-time is curved so severely that light emitted outward from that surface is bent back inward. The escape velocity at the event horizon equals the speed of light, which is another way of saying that space-time curvature there is so extreme that even light following its straightest possible path still curves back toward the black hole. Just outside the event horizon, there's a region called the photon sphere, where light can orbit the black hole in unstable circular paths, bent continuously by the intense curvature of space-time. The shadow of a black hole, the dark region we see in images like the famous Event Horizon Telescope, picture of M87's supermassive black hole, exists because of this extreme light bending. Light that passes close enough to the black hole is captured, unable to escape, creating a dark silhouette. The bright ring surrounding this shadow is light from the accretion disk that has been bent and focused by the black hole's gravity, with some photons having orbited partway around the black hole before reaching the observer, creating multiple images overlaid on each other. Gravitational lensing occurs when light from a distant object passes near a massive object on its way to Earth. The massive object acts as a lens, bending the light and focusing it toward Earth, just as a glass lens bends and focuses light. Galaxies and galaxy clusters containing hundreds of billions or even trillions of times the Sun's mass are particularly effective gravitational lenses. When a massive galaxy cluster lies between Earth and a more distant galaxy, the cluster's gravity bends light from the background galaxy, often creating multiple images, arcs, or even complete rings. Einstein predicted a specific case called an Einstein ring, which forms when the lensing mass, the background light source, and the observer are perfectly aligned. In this configuration, the background object's light is bent equally in all directions around the lensing mass, creating a circular ring of light. Perfect Einstein rings are rare because perfect alignment is unlikely, but numerous partial rings and arcs have been observed where the alignment is close, but not exact. Strong gravitational lensing creates multiple images of the same background object. Light from the source can take different paths around the lensing mass, arriving at Earth from different directions. An observer sees the same galaxy or quasar in multiple locations in the sky simultaneously, each image distorted differently depending on the path the light took. By analysing these multiple images, their positions, brightness and distortions, astronomers can map out the distribution of mass in the lensing object, including the dark matter that can't be seen directly. One of the most famous examples of gravitational lensing revealed itself in the Hubble Deep Field images. A massive galaxy cluster acts as a natural telescope, magnifying and brightening galaxies far behind it. Some of the most distant galaxies ever observed were discovered this way, their light amplified by gravitational lensing to the point where even these incredibly faint, distant objects become visible. Without the magnification provided by the intervening cluster's gravity, these galaxies would be too faint to detect, even with our most powerful telescopes. Weak gravitational lensing is a more subtle effect. Rather than creating obvious multiple images or dramatic arcs, weak lensing slightly distorts the shapes of background galaxies. Each galaxy is stretched and sheared by a tiny amount, usually only a few percent. Individual distortions are impossible to distinguish from the galaxy's natural shapes, but by measuring the shapes of thousands or millions of galaxies and looking for statistical patterns in their distortions, astronomers can map out the distribution of matter, including dark matter, along the line of sight. This technique has become one of the most powerful tools for studying dark matter distribution in the universe. Gravitational lensing also affects the apparent brightness of objects. When a massive object passes between Earth and a more distant star, the foreground object's gravity can focus the background star's light, temporarily brightening it. This gravitational microlensing is used to detect exoplanets. When a star passes in front of another star, the foreground star's gravity creates a brief brightening lasting days to weeks. If the foreground star has a planet, the planet's gravity creates an additional, brief spike in brightness, revealing its presence even though the planet itself is far too faint to see directly. The time light takes to travel along different paths around a gravitational lens can vary. Light taking a longer path around one side of a lensing galaxy arrives later than light taking a shorter path around the other side. For variable sources like quasars, which change in brightness over time, this time delay becomes observable. A brightening in one image of a lensed quasar will appear days, weeks, or months before the same brightening appears in another image, the delay corresponding to the difference in light travel time along the different paths. Measuring these time delays allows astronomers to determine distances to the lensed objects and constrain cosmological parameters like the universe's expansion rate. Space-time curvature near massive objects doesn't just bend light spatially, it also affects light's frequency through gravitational redshift. Light climbing out of a gravitational well loses energy, shifting to longer wavelengths and lower frequencies. Photons emitted from the surface of a white dwarf, neutron star, or near a black hole arrive at Earth redshifted compared to identical photons emitted far from any massive object. This gravitational redshift is distinct from the Doppler shift, caused by motion. It's a consequence of how time itself runs slower in stronger gravitational fields. The ability of gravity to bend light provides one of the most direct ways to test general relativity. Every observation of gravitational lensing confirms Einstein's predictions about how spacetime curvature works. The precise angles at which light bends, the patterns of multiple images, the time delays between images, and the gravitational redshift all match the predictions of general relativity with remarkable accuracy. Alternative theories of gravity make different predictions, and so far, every test has vindicated Einstein's century-old theory. Gravitational lensing has become an essential astronomical tool. It allows us to study the distribution of dark matter by observing how it lenses background galaxies. It magnifies distant galaxies, enabling studies of the early universe that would otherwise be impossible. It reveals exoplanets orbiting distant stars. It measures cosmic distances and the expansion rate of the universe. All of this is possible because massive objects warp spacetime, and light faithfully follows the curves and valleys of that warped geometry. The universe is filled with matter, and that matter curves spacetime everywhere. Light from the most distant galaxies has travelled billions of years to reach Earth, passing countless galaxies, galaxy clusters, and vast expanses of dark matter along the way. Every massive structure the light passes deflects it slightly, creating a cosmic hall of mirrors where every photon's path is bent and redirected many times. The images we see in our telescopes are not straight-line projections from their sources, but rather the accumulated result of countless tiny deflections as light navigates the curved spacetime of our universe. The geometry of the universe itself, on the largest scales, also affects how light travels. If the universe has overall positive curvature, like the surface of a sphere, light paths will eventually converge. If it has negative curvature, like a saddle shape, light paths diverge. Current observations suggest the universe is nearly flat on the largest scales, meaning that, on average, over distances spanning billions of light years, light travels in straight lines. But locally, around every massive object from planets to galaxy superclusters, spacetime curves, and light follows those curves, revealing the intimate connection between matter geometry and the paths that light traces through the cosmos. How planets get their beautiful rings. When you think of planetary rings, Saturn immediately comes to mind, with its magnificent system of bright bands encircling the planet like a cosmic halo. But Saturn isn't alone in possessing rings. Jupiter, Uranus, and Neptune all have ring systems of their own. Though far less prominent, even some asteroids have been discovered with tiny rings circling them. These structures, some broad and bright, others narrow and faint, all share a common origin story rooted in gravity, orbital mechanics, and the sometimes violent history of the solar system. The basic ingredients for planetary rings are surprisingly simple. Countless small particles, ranging from dust grains smaller than smoke particles to chunks of rock and ice the size of houses, all orbiting a planet in a flat disk. What makes rings special isn't the individual particles but their collective behaviour, the way millions or billions of objects interact through gravity and collisions to create structures that can span hundreds of thousands of miles yet be only tens of meters thick. Rings form through several different mechanisms, and understanding these processes means understanding both creation and destruction, both gentle accumulation and catastrophic violence. The first and perhaps most dramatic way rings can form is through tidal disruption. Every planet generates a gravitational field that weakens with distance, and this creates tidal forces on any object orbiting nearby. If you imagine a moon orbiting close to a planet, the side of the moon facing the planet experiences stronger gravity than the side facing away. This difference in gravitational pull creates a stretching force that tries to pull the moon apart. There's a critical distance from any planet, called the Roche limit, inside which these tidal forces become stronger than the moon's own gravity holding it together. Cross this threshold, and the moon cannot remain intact. If a moon migrates inward through various processes, or if it formed inside this limit, it will be torn apart by tidal forces. The material doesn't disappear, it spreads out along the Moon's orbital path, and over time, through collisions and gravitational interactions, it forms a flat ring around the planet. Picture this process in your mind. A small moon, perhaps captured from elsewhere in the solar system or formed in orbit around the planet, slowly spirals inward. Tidal interactions with the planet transfer energy and angular momentum, gradually changing the Moon's orbit. As it crosses the Roche limit, cracks begin to form. Pieces break away, first small fragments, then larger chunks. The Moon doesn't explode dramatically, it comes apart more gradually, like pulling apart a piece of bread. Each fragment continues orbiting the planet independently, and as they collide and break into smaller pieces, they spread into a disk of debris. This process may have created some of Saturn's rings, though the origin of Saturn's ring system remains one of the great puzzles in planetary science. The rings are remarkably bright and rich in water ice, suggesting they might be relatively young, perhaps only a few 100 million years old, rather than as ancient as the solar system itself. One theory suggests that a small icy moon, perhaps 200 miles across, wandered too close to Saturn and was torn apart by tidal forces. The shattered remains spread into the magnificent ring system we see today. Another way rings form is through collisions. Imagine two moons orbiting a planet on paths that eventually intersect, or an asteroid from elsewhere in the solar system crashing into a moon. The impact releases tremendous energy, shattering both objects and ejecting debris into space. Some of this material falls back onto the planet or escapes entirely, but much of it remains in orbit, gradually spreading into a ring. This collision scenario might explain some of the fainter, darker ring systems. Jupiter's rings, for instance, are composed of very small dust particles that appear reddish-brown, suggesting they might come from meteorite impacts onto small inner moons. When a meteorite strikes one of these tiny moons, it kicks up dust that then orbits Jupiter. This dust doesn't stay in the ring system forever. It gradually spirals inward due to interactions with Jupiter's magnetic field and atmospheric drag, but it's constantly replenished by new impacts. Rings can also form from a volcanic activity on moons, though this is a less common mechanism. Jupiter's moon, Io, is the most volcanically active body in the solar system, with eruptions constantly spewing material into space. Some of this material, particularly atoms of sodium and sulfur, forms extended clouds around Jupiter. While not a traditional ring of solid particles, these atomic clouds occupy ring-like regions and show that rings can have diverse origins and compositions. The shepherd moon mechanism plays a crucial role in maintaining and shaping rings once they form. Small moons orbiting just inside or outside a ring can gravitationally interact with ring particles, confining them to narrow bands. Imagine a ring particle in an orbit that would normally cause it to drift outward. As it approaches a shepherd moon, orbiting outside the ring, the moon's gravity tugs on it, altering its orbit and deflecting it back toward the ring. Similarly, a shepherd moon orbiting inside the ring can prevent particles from drifting inward. These gravitational interactions can create remarkably sharp ring edges and can even maintain gaps within ring systems. Saturn's moon Prometheus and Pandora act as shepherd moons for the narrow F ring, one of Saturn's outermost rings. The F ring is only a few hundred miles wide, but thousands of miles long, and without these shepherd moons, it would spread out and dissipate over time. The moon's gravity creates a delicate balance, continuously sculpting the ring into its narrow form. Resonances add another layer of complexity to ring formation and structure. When ring particles orbit at certain specific distances from a planet, their orbital period can be a simple fraction of a moon's orbital period, perhaps half as long, or a third or 2/5. At these resonant locations, the gravitational tugs from the Moon occur at the same point in each orbit, adding up over time and creating powerful effects. Resonances can clear gaps in rings, sweeping particles out of certain orbital paths, or they can concentrate particles, creating narrow ringlets. The Cassini division, the prominent gap in Saturn's rings, visible even through small telescopes from Earth, exists primarily because of a resonance with the Moon Mimas. Particles orbiting in the Cassini division have an orbital period exactly half that of Mimas. The repeated gravitational interactions at this resonance gradually push particles into different orbits, maintaining a gap nearly 3,000 miles wide. The particles within rings are not static. They're constantly colliding with each other, and these collisions shape the ring's structure and evolution. When two chunks of ice collide gently in Saturn's rings, they might stick together, growing larger. But more energetic collisions shatter particles into smaller pieces. There's a balance between these processes, and over time, rings develop a characteristic size distribution of particles, with many small particles and fewer large ones. These collisions also dissipate energy, causing the ring to flatten. Imagine particles orbiting at slightly different inclinations, some tilted a bit relative to others. When they collide, the vertical component of their motion is randomized and gradually damped out through repeated collisions. The result is that rings become extraordinarily thin relative to their width. Saturn's main rings span about 175,000 miles from inner edge to outer edge, yet they're typically only about 30 feet thick, a ratio that's thinner than a sheet of paper if scaled down. Temperature plays a role in ring dynamics as well. Ring particles are heated by sunlight and cooled by radiating infrared energy into space. The equilibrium temperature depends on the particle's size and composition. Larger particles have more thermal inertia and cool more slowly, while smaller particles respond quickly to changes in sunlight. These temperature variations affect how particles stick together when they collide, influencing whether the ring evolves toward larger clumps or maintains a population of smaller particles. The composition of ring particles varies widely between different planets and even within a single ring system. Saturn's rings are predominantly water ice, giving them their high reflectivity and bright appearance. The ice is remarkably pure, though there are trace amounts of rocky material and organic compounds that give some regions a slightly reddish or brownish tint. Uranus's rings, by contrast, are much darker, composed of material that reflects only a few % of the light that hits it. This dark material might be radiation-processed organic compounds, similar to the dark material found on some asteroids and comets. The age of ring systems is a matter of ongoing research and debate. Some rings might be primordial, dating back to the formation of the solar system itself 4.6 billion years ago. These would be rings made from material that was present in the disk of gas and dust from which the planets formed. Material that never coalesced into moons because it was inside the Roche limit. Other rings are clearly much younger, formed by relatively recent collisions or tidal disruptions. Saturn's rings, despite their prominence, might be surprisingly young. Several lines of evidence suggest they could be only a few 100 million years old. They're very bright and icy, lacking the darkening that would come from billions of years of meteorite bombardment. The amount of dust falling into Saturn's atmosphere from the rings suggests they're being depleted at a rate that couldn't be sustained over billions of years. If Saturn's rings are indeed young, it means we're living at a special time in the solar system's history, able to witness these magnificent structures during a brief window of their existence. Rings are not permanent features. They evolve over time, gradually spreading outward or inward, losing material to the planet's atmosphere or to moons, being disrupted by resonances or replenished by new collisions. Some ring systems might last for the lifetime of the solar system, while others might come and go over much shorter timescales. The rings we see today are snapshots in an ongoing process of creation, evolution, and eventual destruction. Even Earth might have had rings at some point in its distant past. Some researchers have suggested that a large impact that created debris in orbit could have temporarily given Earth a ring system that persisted for millions of years before the material either fell back to Earth or coalesced to form the Moon. While speculative, this idea reminds us that ring systems are dynamic features that can appear and disappear throughout a planet's history. The physics governing ring formation operates not just in our solar system, but around planets orbiting other stars as well. Exoplanets with large moon systems or recent collisions might sport ring systems, though detecting such rings at interstellar distances remains incredibly challenging with current technology. The same fundamental processes, tidal disruption, collisions, gravitational interactions, would operate universally, creating rings around any planet where conditions permit, adding layers of complexity and beauty to planetary systems throughout the galaxy. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 times 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, 2 stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances, and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass for the smallest red dwarfs up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection in 2015 came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously. The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion. The chemistry required for life beyond Earth. Life at its most fundamental level is chemistry. Every thought you think, every breath you take, every movement you make results from chemical reactions occurring in your cells. Molecules bind together and break apart. Energy flows from one form to another. And through countless chemical transformations, inanimate matter becomes animate. Dead molecules become living organisms. Understanding what chemistry is required for life beyond Earth means understanding what makes life possible at all. The elements, the reactions, the solvents, and the energy sources that could allow chemistry to cross the threshold from complex but lifeless reactions into something that grows, reproduces, evolves, and ultimately builds civilizations among the stars. Carbon stands at the center of all known life. Every organism on Earth, from bacteria to blue whales, builds its body from carbon-based molecules. Carbon's unique properties make it extraordinarily suitable for life. Each carbon atom can form 4 chemical bonds with other atoms, allowing it to create an immense diversity of molecular structures: long chains, branching trees, rings, and complex 3-dimensional shapes. Carbon bonds with itself strongly enough to create stable molecules, but not so strongly that the bonds cannot be broken and rearranged through normal chemical reactions. This balance allows carbon molecules to be both stable enough to maintain structure and reactive enough to participate in the constant chemical transformations that life requires. Organic chemistry, the chemistry of carbon compounds, encompasses millions of known molecules and potentially billions more that could exist. Carbon combines readily with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create the molecules of life. Proteins, the workhorses of cells that catalyze reactions and build structures, are chains of amino acids linked together, each amino acid containing carbon, hydrogen, oxygen, and nitrogen. DNA and RNA, which store and transmit genetic information, are built from carbon-containing sugars, phosphate groups, and nitrogen-rich bases. Lipids, which form cell membranes and store energy, are long carbon chains with various functional groups attached. Carbohydrates, which provide energy and structural support, are carbon molecules with hydrogen and oxygen in specific ratios. But is carbon truly necessary for life, or is it simply the element that happened to work on Earth? Silicon, sitting directly below carbon in the periodic table, shares many of carbon's properties. Silicon also forms 4 chemical bonds and can create chains and rings similar to carbon. Science fiction has long speculated about silicon-based life, but silicon faces significant challenges. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon compounds tend to be much less diverse than carbon compounds. While carbon forms millions of different molecules, silicon chemistry is far more limited. Most critically, silicon's most common compound is silicon dioxide, quartz, sand, rock, which is extremely stable and insoluble. When silicon burns with oxygen, it creates solid rock rather than a gas that can be easily expelled and recycled. However, silicon-based life might be possible in environments completely unlike Earth. In extremely cold environments where water is frozen solid, silicon chemistry might become more favorable. In the presence of liquid hydrocarbons instead of water, silicon compounds might behave differently, remaining soluble and reactive rather than precipitating as rocks. A frigid world with seas of liquid methane or ethane, like Saturn's moon Titan, might provide conditions where silicon-based biochemistry could operate. Such life would function on completely different principles than Earth's carbon-based organisms, but it might still meet the basic requirements: complexity, self-replication, evolution, and metabolism. Hydrogen plays a crucial role in biochemistry beyond being part of organic molecules. Hydrogen ions, protons, are essential for energy generation in cells. Earth's organisms create differences in hydrogen ion concentration across membranes, then allow the ions to flow back through specialized proteins called ATP synthase, which harness the flowing ions to create ATP, the universal energy currency of life. This process, called chemiosmosis, powers nearly all life on Earth and represents a fundamental way of coupling energy sources to useful work. Any biochemistry, whether carbon-based or otherwise, would need some mechanism for capturing and storing energy, and hydrogen's simple chemistry makes it an excellent candidate for this role, regardless of the specific biochemistry involved. Oxygen serves multiple roles in Earth's biochemistry. It's part of water, part of most organic molecules, and it serves as the final electron acceptor in cellular respiration, the process by which organisms extract energy from food. When glucose is metabolized with oxygen, the reaction releases large amounts of energy that cells capture in the chemical bonds of ATP. This oxygen-based metabolism, called aerobic respiration, is far more efficient than metabolism without oxygen. However, oxygen was not always available on Earth. For the first 2 billion years or more, Earth's atmosphere contained very little free oxygen, and early life functioned without it, using anaerobic metabolism based on different chemical reactions. Some organisms today still live without oxygen, in deep ocean sediments or the guts of animals, using sulfur compounds, nitrates, or iron as alternatives to oxygen. Life beyond Earth might never develop oxygen-based metabolism if oxygen never becomes abundant in the atmosphere. Planets orbiting red dwarf stars might have difficulty accumulating oxygen because ultraviolet light from the star, which on Earth helps break apart water molecules in the upper atmosphere, leading to oxygen accumulation, is less intense. Life on such worlds might remain dependent on anaerobic metabolism indefinitely, which would likely limit the size and energy consumption of organisms. Active, energy-intensive lifestyles, like those of birds or mammals, require the high energy output that only oxygen metabolism provides. Alien life using alternative metabolic pathways might be restricted to smaller, slower, lower energy forms. Nitrogen is essential for proteins and nucleic acids. It's found in amino acids and in the bases that make up DNA and RNA. Nitrogen chemistry is complex and often difficult. Nitrogen gas in the atmosphere consists of 2 nitrogen atoms triple bonded together, making it very stable and unreactive. Converting atmospheric nitrogen into biologically useful forms, a process called nitrogen fixation, requires significant energy or specialized catalysts. On Earth, certain bacteria can fix nitrogen using enzymes containing iron and molybdenum. Lightning also fixes nitrogen by forcing nitrogen and oxygen to react in the high-energy conditions of electrical discharge. Life on other planets would need some source of biologically available nitrogen, either through similar fixation processes or through nitrogen already present in reactive forms. Phosphorus plays a unique and critical role in biochemistry. It's part of the backbone of DNA and RNA, linking the sugar molecules together into the long chains that store genetic information. It's also central to ATP, the molecule that stores and transfers energy in cells. Phosphate groups can be added to and removed from molecules to regulate their activity, serving as switches that turn cellular processes on and off. There is no obvious substitute for phosphorus in these roles. Unlike carbon, nitrogen, and oxygen, which are abundant in the universe, phosphorus is relatively rare, created only in certain types of stellar processes. A planet poor in phosphorus might struggle to develop complex life, at least of the kind we would recognize. Sulfur contributes to protein structure through disulfide bonds, connections between sulfur atoms in different parts of a protein that help the protein fold into its proper 3-dimensional shape. Some organisms use sulfur compounds in their metabolism instead of or in addition to oxygen. Near hydrothermal vents on Earth's ocean floor, bacteria oxidize hydrogen sulfide, the compound that smells like rotten eggs, to generate energy. Entire ecosystems build on these chemosynthetic bacteria, demonstrating that sunlight and photosynthesis are not necessary for life. An alien world with extensive volcanic or hydrothermal activity could support life based on sulfur chemistry, even in complete darkness. Trace elements, though needed in tiny amounts, are essential for many biological processes. Iron is central to hemoglobin, the protein that carries oxygen in blood, and to many enzymes involved in energy metabolism. Magnesium sits at the center of chlorophyll molecules, enabling photosynthesis. Zinc, copper, manganese, and other metals serve as cofactors for enzymes, helping catalyze reactions that would otherwise proceed too slowly to sustain life. An alien biochemistry would likely require its own set of trace elements, perhaps using metals common on its world but rare on Earth, or finding entirely different solutions to catalysis and molecular structure. Water serves as the solvent for biochemistry on Earth, the medium in which all cellular chemistry occurs. Water has remarkable properties that make it ideal for life. It remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at Earth's atmospheric pressure. It has a high heat capacity, meaning it resists temperature changes, which helps organisms maintain stable internal temperatures. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other, allowing water to dissolve ionic compounds and interact with many different types of molecules. The hydrogen bonds between water molecules create surface tension, capillary action, and the unusual property that ice floats on liquid water, a characteristic that has profound implications for life in oceans and lakes. But is water necessary for life? Or might other liquids serve as solvents for alternative biochemistries? Ammonia has been proposed as a possible alternative. Ammonia remains liquid at much colder temperatures than water. It freezes at -78 degrees Celsius and boils at -33 degrees Celsius at Earth's atmospheric pressure. A very cold planet, too cold for liquid water, might have lakes or oceans of liquid ammonia. Ammonia shares some of water's properties. It's polar, can form hydrogen bonds, and dissolves many substances. However, ammonia is a less effective solvent than water for many compounds, and the biochemistry that could operate in liquid ammonia would necessarily be very different from Earth's water-based life. Methane and ethane, though non-polar and very different from water, exist as liquids on Titan, Saturn's largest moon. Titan has lakes and rivers of liquid hydrocarbons on its surface, creating a hydrological cycle remarkably similar to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. Could life exist in these hydrocarbon lakes? The chemistry would be completely unlike anything on Earth. Reactions that occur readily in water might not occur at all in methane, while entirely different reactions become possible. Cell membranes would need to be built from different molecules. The lipid membranes used by Earth's cells wouldn't function in liquid methane. Energy metabolism would follow different pathways. But some scientists argue that the sheer strangeness of Titan's environment doesn't preclude life, only life that operates on unfamiliar principles. Supercritical fluids represent another possibility. Under high pressure and high temperature, substances enter a supercritical state where the distinction between liquid and gas breaks down. Supercritical carbon dioxide, for instance, behaves as both liquid and gas simultaneously, with properties of each. Deep beneath the surfaces of certain planets, conditions might create supercritical water or other supercritical fluids that could potentially serve as solvents for exotic biochemistries operating under extreme conditions. Energy sources drive all biochemistry. On Earth, sunlight powers most ecosystems through photosynthesis. Plants and photosynthetic bacteria capture light energy and use it to build organic molecules from carbon dioxide and water. These organic molecules then flow through food chains, ultimately providing energy for all other organisms. But many alternative energy sources exist. Chemical energy from redox reactions, where electrons transfer from one molecule to another, can sustain life in complete darkness. Radioactive decay in a planet's interior could provide steady energy through the heat it generates, potentially supporting life in subsurface environments for billions of years, even if the star above has long since died. The origin of life, the transition from complex chemistry to living organisms, requires conditions where organic molecules can form, concentrate, and begin the process of self-replication and evolution. On Earth, this might have occurred in tidal pools, in hydrothermal vents, in ice, or even in the atmosphere. The exact location and mechanism remain uncertain, but the chemistry required involves forming increasingly complex molecules from simpler precursors, eventually creating molecules capable of catalyzing reactions, including their own replication. This requires an energy source to drive uphill reactions that create complexity from simplicity, fighting against entropy. It requires some form of containment, membranes or surfaces, to concentrate molecules and create distinct chemical environments. And it requires time for random chemical processes to explore countless possibilities until self-replicating systems emerge. The universality of certain chemical principles suggests that life elsewhere, no matter how alien, would still obey the same rules of chemistry and thermodynamics that govern Earth's life. All life must extract energy from its environment and use that energy to create and maintain complex organization. All life must reproduce, passing information to offspring. All life must evolve through variation and selection. These requirements constrain the chemistry of life, regardless of what specific molecules are involved. Carbon is not the only possible basis for complex chemistry, water is not the only possible solvent, and oxygen is not the only possible energy source, but any living system must solve the same fundamental chemical problems: how to capture and store energy, how to build complex molecules, how to replicate information, and how to maintain organization in a universe that constantly tends toward disorder. The chemistry required for life beyond Earth encompasses the familiar carbon, water, proteins, and DNA, and the exotic silicon biochemistry in hydrocarbon seas, life in supercritical fluids, using metals we've never heard of, organisms metabolizing on reactions we've never imagined. The universe provides the raw materials everywhere: hydrogen from the Big Bang, heavier elements forged in stars and scattered through supernova explosions. Every planet, moon, and asteroid contains chemistry, happening constantly through radiation, temperature gradients, and the simple mixing of different compounds. Whether that chemistry crosses the threshold into life depends on having the right combination of elements, solvents, energy sources, and time, ingredients that might exist on countless worlds throughout the cosmos, waiting for chemistry to become biology in endless variations on the theme of life. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival: in boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of barophils, pressure-loving organisms, suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter. though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environments can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome. Given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found, vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The lighthouse stars that spin incredibly fast. In 1967, a graduate student named Jocelyn Bell noticed something peculiar in her radio telescope data, a signal that pulsed with extraordinary regularity, repeating every 1.3373 seconds. The precision was so remarkable that she and her advisor initially wondered whether they had detected an artificial signal from an extraterrestrial civilization. They jokingly called it LGM-1 for Little Green Men. But as more of these pulsing sources were discovered, each with its own precise period, it became clear they were witnessing something natural, but entirely unexpected. Rapidly spinning neutron stars whose beams of radiation sweep across Earth like cosmic lighthouses. These objects, now called pulsars, are among the most extreme objects in the universe. They are neutron stars, the collapsed cores of massive stars that exploded as supernova, compressed to densities where a sugar cube-sized amount of material would weigh as much as a mountain. What makes pulsars special is not just their incredible density, but their rotation. These stars spin at rates that seem impossible for something so massive. Many complete one rotation in less than a second, some in mere milliseconds, whirling around hundreds of times per second while containing more mass than the Sun. The story of a pulsar begins with the death of a massive star. When a star, at least 8 times more massive than the Sun, exhausts its nuclear fuel, its core collapses catastrophically. The outer layers rebound and explode outward as a supernova, but the core continues collapsing until nuclear forces halt the compression, creating a neutron star about 12 miles across. This neutron star inherits the angular momentum of the original star's core, but because the radius has shrunk by a factor of perhaps 100,000, the rotation rate increases dramatically through conservation of angular momentum. Imagine a figure skater pulling their arms inward during a spin, rotating faster and faster as their radius decreases. The collapsing stellar core undergoes the same process, but on a far more extreme scale. A star that was rotating once every few weeks might produce a neutron star that rotates several times per second. The fastest spinning pulsar known, designated PSRJ 1748-2446 AD, rotates 716 times per second. At its equator, the surface is moving at approximately 70,000 miles per second, nearly 1/4 the speed of light. At these speeds, the neutron star is ablate, bulging significantly at its equator due to centrifugal forces, yet it holds together through the tremendous strength of neutron degenerate matter and its own crushing gravity. The lighthouse effect that makes pulsars detectable comes from their magnetic fields. Neutron stars possess the strongest magnetic fields known in the universe, typically 1 trillion times stronger than Earth's magnetic field. When the core of the parent star collapses, any magnetic field present is compressed and amplified tremendously. This field doesn't simply shrink, it gets concentrated into a much smaller volume, intensifying to values that would tear apart atoms and polarize the vacuum of space itself. This intense magnetic field is not aligned with the neutron star's rotation axis. Just as Earth's magnetic poles don't coincide with its geographic poles, a neutron star's magnetic axis is typically tilted relative to its spin axis. Charged particles, primarily electrons and positrons, are accelerated along the magnetic field lines, particularly near the magnetic poles. These particles, accelerating at relativistic speeds, emit intense beams of radiation through a process called synchrotron radiation. The beams emerge from the magnetic poles, creating two searchlights that sweep through space as the neutron star rotates. When one of these beams sweeps across Earth, we detect a pulse of radio waves, X-rays, or gamma rays, depending on the pulsar's characteristics. The pulse arrives with extraordinary regularity. The best pulsars keep time as accurately as atomic clocks, varying by only microseconds over years. This precision exists because the neutron star is such a stable rotator. Its enormous rotational inertia, combined with its extreme density and rigidity, means that nothing can easily change its spin rate. It's like an enormous cosmic flywheel, storing vast amounts of rotational energy and releasing it only very gradually. The radio emission mechanism is complex and still not completely understood, despite decades of study. The acceleration of charged particles near the magnetic poles creates a cascade of electromagnetic radiation. These particles follow the curved magnetic field lines, and as they accelerate, they emit photons. These photons can interact with the intense magnetic field to create more particle-antiparticle pairs, which then accelerate and create more photons, building up a cascade that produces the intense radio emission we detect. The region where this occurs, just above the magnetic poles, is called the polar cap, and it's here that the lighthouse beams originate. Not all pulsars emit at the same wavelengths. Some are primarily radio pulsars, detected through their radio emission. Others are X-ray pulsars, emitting primarily high-energy X-rays. A few emit gamma rays, the most energetic form of electromagnetic radiation. Some pulsars emit across the entire electromagnetic spectrum simultaneously, creating pulses detectable from radio waves through gamma rays. The emission properties depend on factors like the neutron star's age, its magnetic field strength, its rotation rate, and the environment surrounding it. Young pulsars, recently formed in supernova explosions, tend to rotate faster and have stronger magnetic fields than old pulsars. The Crab pulsar, formed in a supernova observed by Chinese astronomers in 1054 AD, rotates 30 times per second and emits powerfully across the electromagnetic spectrum. It sits at the center of the Crab Nebula, the expanding remnant of that supernova explosion, and its intense radiation illuminates the surrounding nebula, causing it to glow. The pulsar acts like a cosmic power station, converting its rotational energy into electromagnetic radiation and high-energy particles that energize the nebula. Pulsars slow down over time, gradually losing rotational energy. This spin-down occurs because the rotating magnetic field acts like a brake. The magnetic field lines extend far into space, and as they rotate with the neutron star, they drag charged particles along, accelerating them and carrying away energy and angular momentum. This magnetic braking gradually robs the neutron star of its rotational energy. A young pulsar might slow down measurably over just a few years, while an old pulsar might take millions of years to show detectable changes in its period. The rate at which a pulsar slows down reveals information about its magnetic field strength and age. By measuring the current rotation period and the rate of change of that period, astronomers can estimate how long the pulsar has been spinning down and how much longer it will continue to pulse before its rotation becomes too slow and its magnetic field too weak to generate detectable radiation. Most pulsars have lifetimes of tens of millions of years as active radio sources before they fade from detectability, though the neutron star itself continues existing and spinning, just no longer producing observable pulses. Some pulsars experience sudden speed-ups, called glitches. The neutron star's rotation rate, which normally decreases steadily, suddenly increases slightly, then resumes its gradual slowdown. These glitches are thought to occur because the neutron star's interior contains a superfluid, a state of matter with zero viscosity that can flow without any resistance. This superfluid rotates faster than the star's crust, and occasionally, angular momentum transfers suddenly from the superfluid to the crust, causing the observable spin-up. Glitches provide rare windows into the exotic physics occurring inside neutron stars, where matter exists in states impossible to recreate in laboratories. Millisecond pulsars present a fascinating puzzle. These pulsars rotate hundreds of times per second, far faster than young pulsars, yet they're old neutron stars, billions of years old. How can an old pulsar be spinning so fast? The answer lies in a process called recycling. A millisecond pulsar was once a normal pulsar that slowed down over hundreds of millions of years. But if it's in a binary system with a companion star, and that companion evolves to become a giant star, matter can flow from the companion onto the neutron star. This infalling matter carries angular momentum, spinning up the neutron star like water hitting a water wheel. Over millions of years, the neutron star is spun up to millisecond periods, recycled into a new youth of rapid rotation. Some pulsars are part of binary systems where we can directly observe this process happening. X-ray binary pulsars show X-ray pulses as the neutron star accretes material from its companion. The infalling material, heated to millions of degrees before hitting the neutron star's surface, emits intense X-rays. These systems are the evolutionary precursors to millisecond pulsars, caught in the act of being spun up by accretion. The most rapidly rotating pulsars ever discovered are all millisecond pulsars, and some of them are in dense globular clusters where stars are packed closely together. The high stellar density in these clusters makes binary interactions more likely, creating environments where many neutron stars can be recycled through accretion. Some globular clusters contain dozens of millisecond pulsars, creating a cosmic percussion section where numerous neutron stars pulse at different rates, each one a precisely ticking clock with its own unique period. Pulsars can also have planets. The first exoplanets ever discovered orbit a pulsar called PSRB 1257+12. These planets were detected through tiny variations in the pulsar's timing. As the planets orbit, their gravity tugs the pulsar slightly back and forth, causing the pulses to arrive slightly early or late in a periodic pattern. The planets orbiting this pulsar are thought to be second-generation worlds, formed from the debris of the supernova explosion that created the neutron star, or possibly from material that later fell back onto the system. These are harsh worlds, bathed in intense radiation from the pulsar, utterly unlike the planets orbiting normal stars. Binary pulsars, where two neutron stars orbit each other, provide extraordinary laboratories for testing general relativity. The orbital motion of such systems produces gravitational waves that carry away energy, causing the orbit to shrink over time. The rate of orbital decay matches Einstein's predictions with incredible precision. The first binary pulsar discovered, PSRB 1913+16, provided the first indirect evidence for gravitational waves, Decades before, gravitational wave detectors directly observed them from merging black holes and neutron stars. The regularity of pulsar timing has practical applications. Astronomers use networks of millisecond pulsars across the galaxy as a cosmic timing array, watching for tiny correlated deviations in their pulse arrival times that would indicate gravitational waves passing through the galaxy. These pulsar timing arrays are sensitive to gravitational waves with much longer wavelengths than ground-based detectors can observe, potentially detecting the gravitational wave background from supermassive black hole mergers throughout the universe. Pulsars also serve as natural laboratories for extreme physics. The conditions near their surfaces, intense magnetic fields, extreme gravity, densities exceeding that of atomic nuclei, cannot be reproduced on Earth. By observing pulsars across the electromagnetic spectrum and measuring their properties precisely, physicists learn about how matter behaves under conditions that push the boundaries of our physical theories, testing general relativity in strong gravitational fields and probing the equation of state of matter at nuclear densities. These spinning neutron stars, these cosmic lighthouses flashing their beams across the universe, represent one endpoint of stellar evolution. From the violent collapse of a massive star's core emerges an object so dense, so rapidly spinning, so strongly magnetized that it challenges our understanding of physics. Each pulse detected from a pulsar is a message from one of the universe's most extreme environments, a precisely timed signal carrying information about physics at the edge of what's possible, reminding us that the universe contains objects and phenomena far stranger than we could have imagined before we discovered these remarkable, spinning stellar remnants. The universal laws that would shape all life. While alien life might look nothing like Earth's organisms, using different chemistry, different genetic molecules, different metabolic pathways, certain fundamental principles would constrain and shape all life everywhere in the universe. These universal laws arise not from biological specifics, but from physics, chemistry, thermodynamics, and information theory, disciplines that operate identically throughout the cosmos. Understanding these universal constraints reveals what all life, no matter how alien, must have in common, and what fundamental challenges every living system must solve to exist, grow, reproduce, and evolve on any world, under any star, in any galaxy. The laws of thermodynamics govern all physical processes, and life is no exception. The second law of thermodynamics states that entropy, disorder, tends to increase in closed systems. Left to themselves, organized structures break down, concentrated energy disperses, and order gives way to chaos. A sandcastle erodes, a hot cup of coffee cools to room temperature. Complex molecules break apart into simpler ones. This universal tendency toward disorder creates life's fundamental challenge. Living organisms are highly organized, low-entropy systems existing in a universe that constantly pushes toward disorder. Maintaining biological organization requires constant energy input to fight against entropy's relentless pull. All life, everywhere in the universe, must extract energy from its environment and use that energy to maintain and build ordered structures. On Earth, photosynthetic organisms capture energy from sunlight. Other organisms obtain energy by consuming and metabolizing food, breaking down the chemical bonds in organic molecules and harnessing the released energy. Chemosynthetic organisms extract energy from inorganic chemical reactions. The specific mechanisms vary enormously, but the underlying requirement is universal. Every living thing must have a metabolism, some way of extracting usable energy from its surroundings to power the processes that maintain life. This creates a fundamental constraint. Life can only exist where energy flows. Environments in perfect thermodynamic equilibrium, where no energy gradients exist, cannot support life. Life requires disequilibrium, a hot vent and cold water, sunlight falling on chemical systems, redox gradients between different chemical species. These disequilibria provide the energy flow that life harnesses. Alien life, no matter what chemistry it uses or what planet it inhabits, must exist in regions where energy flows from higher to lower energy states, capturing some of that flowing energy to power metabolism. Evolution through natural selection represents another universal principle. Any system capable of reproduction, variation, and selection will inevitably evolve. This is not a biological principle, but a logical and mathematical necessity. If organisms reproduce, creating copies of themselves, and if those copies are not perfect but contain variations, and if some variants survive and reproduce more successfully than others due to those variations, then the population will change over generations as successful variants become more common and unsuccessful variants decline. This is evolution by natural selection, and it operates on any replicating system with heritable variation subject to selection pressures. Alien life would therefore inevitably evolve, becoming adapted to its environment through countless generations of selection favoring organisms better suited to local conditions. The specific adaptations would differ. Alien organisms might evolve features we've never imagined, but the process would be the same. Evolution is not optional or unique to Earth. It's a fundamental consequence of how replicating systems behave over time. Any civilization that discovers alien life would find that life has been shaped by evolution just as Earth's life has been shaped, even if the resulting organisms look and function completely differently. This evolutionary principle creates a corollary, convergent evolution, where different lineages independently evolve similar solutions to similar problems, occurs because physics and chemistry constrain the possible solutions. Eyes evolved independently many times on Earth because detecting light provides such valuable information, and focusing light onto photosensitive cells is the most effective way to create detailed images. Streamlined body shapes evolved independently in fish, dolphins, ichthyosaurs, and penguins because that shape minimizes drag in water. These convergences occur because physical laws determine what works well in given circumstances. Alien life would show similar convergences. Any organism that needs to move through fluid efficiently would likely evolve some form of streamlined shape because physics demands it. Any organism that needs to detect electromagnetic radiation would likely evolve some structure that captures and focuses that radiation. The details would vary. Alien eyes might have 10 light-sensing structures instead of 2, might sense infrared instead of visible light, might use completely different photosensitive molecules than Earth organisms. But the basic function would be similar because the physics of light detection operates universally. Information storage and transmission represent another universal requirement. Living organisms must store information about how to build and maintain themselves, and they must transmit this information to their offspring. On Earth, this information is stored in DNA and RNA sequences, but the specific molecule doesn't matter. What matters is that some physical system must encode instructions that can be copied and passed to the next generation, and these instructions must contain enough information to specify the organism's structure and function with sufficient detail that offspring resemble parents. The amount of information required sets minimum limits on the complexity of genetic systems. A viable organism cannot be specified by just a few bits of information. It requires substantial information content to encode even the simplest metabolic pathways, structural components, and reproduction mechanisms. Earth's simplest free-living bacteria have genomes containing roughly 500,000 base pairs, encoding about 500 genes. This represents the approximate minimum information content for independent life under Earth conditions. Alien life might require more or less information depending on environmental complexity and metabolic strategies. But some minimum threshold exists below which organisms cannot encode enough instructions to function and reproduce reliably. The fidelity of information copying, how accurately genetic information is replicated, creates a universal trade-off. Perfect copying with zero errors would prevent evolution because no variation would arise. But too many copying errors would lead to error catastrophe, where genetic information degrades faster than selection can eliminate harmful mutations. There exists an optimal error rate that balances stability and evolvability, allowing organisms to maintain essential functions while still generating the variation necessary for adaptation. Alien genetic systems would face this same trade-off and would likely evolve error rates in a similar optimal range, regardless of what molecules store their genetic information. Physical scaling laws constrain organism size and structure. The strength of materials scales with cross-sectional area, proportional to the square of linear dimensions, while weight scales with volume, proportional to the cube of linear dimensions. This means that, as organisms get larger, their weight increases faster than their structural strength. A human scaled up to 10 times normal height would weigh 1,000 times as much, but would have bones only 100 times as strong. The skeleton would collapse under the weight. This scaling law explains why large land animals have thick, sturdy legs relative to their body size, while small animals have gracile limbs. Elephants have legs like pillars. Mice have delicate, thin legs. An alien planet with higher gravity would have organisms with even thicker, stronger structural supports relative to their size. A lower gravity planet would allow more slender structures. But the mathematics of scaling operates universally, constraining what body plans are physically possible at different sizes. Surface area to volume ratio creates another universal constraint. Small organisms have large surface area relative to their volume, making heat loss rapid and making diffusion effective for transporting materials. Large organisms have small surface area relative to volume, retaining heat more effectively but requiring specialized circulatory systems because diffusion becomes inadequate for transporting nutrients and waste across large distances. These scaling relationships would govern alien life, just as they govern Earth life, determining which transport mechanisms are necessary at different sizes and what thermal regulation strategies are required. Chemical reaction rates depend on temperature, creating universal constraints on metabolism. Higher temperatures speed up chemical reactions exponentially. A rule of thumb is that reactions roughly double in rate for every 10-degree increase in temperature. This means organisms in hot environments can have faster metabolisms, grow more quickly, and potentially think faster if they're intelligent. Organisms in cold environments have slower metabolisms, grow more slowly, and would process information more slowly if conscious. These temperature effects on reaction kinetics are universal, affecting any chemistry-based life regardless of specific biochemistry. Diffusion rates determined by physics limit how large cells can be. Molecules move through cells by random thermal motion, diffusion. This process is slow. A molecule might take seconds or minutes to diffuse across a large cell. This limits cell size because cells need to move nutrients, wastes and signals around internally, and diffusion becomes prohibitively slow beyond certain sizes. Earth's largest cells are only about 1 millimeter across, and most are much smaller. Alien cells, regardless of their chemistry, would face similar diffusion limits unless they evolved active transport mechanisms, like Earth's eukaryotic cells use, with molecular motors moving cargo along cellular highways. The speed of light creates absolute limits on information transfer. No signal can travel faster than light, which means there are minimum response times for any organism based on its size. An organism the size of a bacterium, a few micrometers, experiences internal light travel times of trillionths of a second, essentially instantaneous. But a hypothetical, planet-sized organism would experience light travel times of tens of milliseconds from one side to the other, creating unavoidable delays in communication and coordination between distant parts. Very large organisms would necessarily be slow to respond to stimuli and might need decentralized control systems because centralized coordination becomes impractical when signal delays become significant. Energy efficiency sets ultimate limits on what metabolic processes are possible. Chemical reactions have maximum energy yields determined by the bonds being broken and formed. An organism cannot extract more energy from a reaction than the chemistry allows. This means life on worlds with limited energy availability, dim stars, deep subsurface environments, chemical poor conditions would necessarily have low energy lifestyles, growing slowly and reproducing infrequently. High energy environments allow active, energetic lifestyles, but also demand mechanisms to dissipate excess heat. Water's unique properties, while not absolutely required for life, make it an excellent solvent for biochemistry. Water remains liquid across a convenient temperature range, has high heat capacity that buffers against temperature changes, expands when freezing so ice floats, acts as a polar solvent that dissolves ions and many organic molecules, and participates in many biochemical reactions. While life could potentially use other solvents, liquid ammonia, methane, supercritical carbon dioxide, any solvent must have properties that allow complex chemistry to occur, molecules to dissolve and interact, and cellular compartments to form. Not many liquids have the right combination of properties, making water-based life probably more common than exotic alternatives, though not exclusively so. Complexity emerges hierarchically, with simple components combining into more complex structures, which combine into still more complex systems. Atoms form molecules. Molecules form macromolecules. Macromolecules form cellular structures. Cells form tissues. Tissues form organs. Organs form organisms. Organisms form ecosystems. This hierarchical organization seems to be how complexity arises universally, because building complex systems directly from simple components becomes unmanageable beyond certain complexity levels. Modular hierarchical construction allows greater complexity to be achieved and maintained. Alien life would likely show similar hierarchical organization, even if the specific components at each level differ completely from Earth's biological hierarchy. Darwinian selection favors efficiency. Organisms that use resources more efficiently have advantages over wasteful competitors. This drives evolution toward optimized solutions within physical constraints. Alien life would similarly be shaped by selection for efficiency, though what constitutes efficient depends on environmental context. In energy-rich environments, speed might matter more than efficiency. In energy-poor environments, extreme efficiency becomes essential for survival. But the general principle that natural selection tends to optimize organisms for their specific circumstances within physical constraints operates universally. The universal laws that would shape all life encompass thermodynamics, demanding that life exist only where energy flows, and that organisms extract energy to maintain order against entropy. Evolution, through natural selection, being an inevitable consequence of imperfect replication with variation. Information requirements, setting minimum complexity thresholds, scaling laws constraining size and structure, chemical kinetics determining metabolic rates, and physical limits on signal speeds, and diffusion rates imposing fundamental constraints on how large and fast organisms can be. These laws operate identically throughout the universe, guaranteeing that while alien life might look and function completely differently from Earth's organisms in countless details, the fundamental principles governing life's existence, evolution, and physical limitations would be the same everywhere, creating a common framework that all life must operate within, regardless of whether it's based on carbon or silicon, DNA or something entirely different, oxygen metabolism or sulfur chemistry. Because physics and chemistry and thermodynamics and information theory operate identically on every world orbiting every star in every galaxy, creating universal constraints that shape all possible forms of life into entities that must harvest energy, maintain organization, store and transmit information, and evolve through selection, making these principles the true universals of biology that would apply to any living thing humans might ever encounter.